Hello, in this lecture we are going to in this lecture we are going to continue with the discussions we were doing in the previous lecture, and let us see the case of. So in this particular lecture we are going to see the case of potential outside. So for example, in the most general way, if I say understand there may be a possibility that at potential even at infinite may not be infinite. Uh, I'll give you that particular case also if time permits. But overall, for most of the cases, we know that potential would be zero at infinite. I mean, this is what we take. The reference potential would be uh, zero at infinite. But there are cases. For example, if your uncharged sphere is placed in an external electric field. So in that particular case, if your net external field is going, the lines are going even as like till infinity also. So then there's a possibility. Then there would be the case that your potential would be infinite at infinite as well. So you will not have potential being zero at infinite. So for most of the cases, I can do this. So for most of the cases, so now if potential is specified v naught theta, is potential is specified v naught theta on this like surface. So v naught theta is specified on the surface. So it is specified on the surface as v naught theta. Now what to do? If it is specified v naught theta on the surface, and we want to find potential anywhere outside. We want to find potential anywhere outside. So what we'll do, we'll use the same kind of thing, but only thing is that the potential outside would be given by summation BL upon R raised to power L PL cos theta. Now continuity condition gives me that the potential at R would be equals to what? It will be simply summation BL upon, sorry, this is I think L plus 1. This will be like BL upon R raised to power L plus 1, and this will be like PL cos theta. Is that clear? And this is like equals to what? V naught theta. Now what I'll do, I will simply integrate both of the side by PL dash, like I'll multiply both of the side by PL dash cos theta sin theta and integrate it from 0 to pi. So what I'll do, I'll simply integrate it from 0 to pi, and as I mentioned in the previous lecture also, it will only give me a non-zero integral, and that would be 2 upon 2L plus 1 if L is equal to L dash. So what I'll get, I'll simply get BL upon 2L plus 1, sorry, 2 upon 2L plus 1 BL, and then I will get, I think, uh, 1 upon R raised to power L plus 1. Is that clear? 2 upon 2L plus 1, 2 upon 2L plus 1, and this R key power L plus 1 is a constant, so this will also come out. Is that clear? And this will be equals to what? This will be equals to integration 0 to pi, and this will be like V naught theta, and then you have this PL cos theta, and then you have sin theta d theta. I think it is clear. So if my potential is specified V naught on the surface, I can find potential outside, and that is equals to summation VL upon R raised to power L plus 1. Okay, you're not able to hear properly. Just give me a minute.
Now it's clear.
अभी आवाज clear है? ठीक है. So like it will be like summation VL upon R raised to power L plus 1 PL cos theta, where your BLs are given by I think it is 2L plus 1 upon 2 R raised to power L plus 1, and this is integration from 0 to pi, and this is V naught theta PL cos theta sin theta d theta. So this is how you're going to get your BLs. So once you know your BLs, then you're able to identify your potential anywhere outside. You're able to identify potential anywhere outside. Is that clear? And this V naught theta is the potential which is specified on the surface. Okay. So like BL is equal to 2L plus 1 upon 2 R की power L plus 1 integration from 0 to pi V naught theta PL cos theta sin theta dθ. This is your BLs. You can replace your BL here and you'll find the potential anywhere outside. Is that clear? And this is the most general result. I mean, this is the most general result. I'm just giving it to you so that if somebody asks you in an interview, this will be the answer. Now, and now understand that if my potential is given as phi naught cos square theta on the surface, and if I want to find potential anywhere outside the sphere, like if my potential is given as phi naught cos square theta on the surface, and if I have to find potential anywhere outside, what I have to do? See, potential anywhere outside is written as I've given it to you like BL upon R raised to power L plus 1 PL cos theta. This is potential anywhere outside. And I know that on my surface, it is given as phi naught cos square theta. On the surface, I know my potential is phi naught cos square theta. And since I know that my potential is continuous, I will simply replace R equal to capital R. So if I replace R equal to capital R, I will find potential on the surface. So potential on the surface is given by this, and given to me that this potential is phi naught cos square theta. So overall, what I'll do, I will equate both of these terms, and I will find this BL. I will find these BL, and once my BLs are known, I'll replace this BL all over again, and I'll find potential outside anywhere as a function of R and theta. Is that clear?
Yes, sir.
Okay. Okay. Good. So now just equate them up, and now here you do not have a quadratic term, you do not have a linear term, you have a quadratic term given to you. So what I would do, I would simply equate them up. So I'll equate them up, and if I equate them up, I'll get B naught upon R, and then you have this P1 cos P. So forget about it. You place L equal to 1, this will be like B1 upon R square. This is cos theta, and then you have some B2 upon R cube, and then you have 3 cos square theta minus 1 upon 2. Forget about the terms like आगे वाले terms को भूल जाओ, because there's a possibility that cos square theta will occur. Not possibility, I would say that it will occur in P4, I guess, if I'm not wrong. P4, there's a possibility that it will occur. Just give me a minute. I think P4 cos theta I've written. Okay, there is a quadratic, but also understand that there is no biquadratic term. Since there is no biquadratic term, so P4 would go 0. So overall, don't go to that level. If you want to go, you can do that thing, but it will be like, eventually you'll get whatever I'm saying right now. But remain cautious on these things. So that is why I'm saying at least till order 4, you should remember. Otherwise, it will give you, otherwise you are left with no other option than to integrate both of sides by PL cos theta, sin theta, and then you have to do it in like, ultimately it will end, you will end up getting this only. So don't worry. So now just equate the, like you just write the terms in a proper manner. So I will write constant terms first, then I will write linear terms here. This is my linear term, and this is my quadratic term. So this is my quadratic term. So from here, your quadratic term, you know that your B2 you'll get. You know that there is no such term in cos theta, so your B1 would go from B1 would become 0. So forget about it. Now you're left with only one option, that you have this B naught and you have this B2. So you have to find this B2 and you have to find this B naught. B2, you know that B2 would be equals to what? B2 will be equals to 2 phi naught upon 3. I think there is some, sorry, no, B2 क्या होगा? एक phi naught R cube भी तो होगा ना? So B2 will be 2 phi naught R cube upon 3. And from B2, if once you know your B2, you'll find this term also, because this term is 0, there's no constant term there. So your B naught is simply B2 upon 2R square. So you'll simply get phi naught R upon 3. So your B naught is this, B2 is this, B1 is 0, and BL is 0 for all other L. Is that clear? So overall, I will write my potential anywhere outside can be written as summation B. So all those things I'm not going to repeat. So that will be like phi naught R upon 3, and then you have small r, phi naught R upon 3, and then you have the small r, and P naught cos theta is 1. Forget about it. And this B2 will come out, come at so I will write simply 2 phi naught upon 3, and this will be, I think, small r cube, and this will be capital R cube here, and then you have this P2 cos theta. So I'll write 3 cos square theta minus 1. Is that clear? So V anywhere outside is given by this. So overall, I will write my V outside. थोड़ा सा इसको symmetrically set कर लेते हैं. So this will be like phi naught upon 3 R upon capital R upon small r plus 2 phi naught upon 3 cos square theta minus 1 upon 2, and then you have this R upon small r का whole cube. So potential outside, potential inside, like this is what I have taught you. So both of these things you can do. Are you getting my point, or are you not getting my point at all?
Bhaiya.
Okay, so this is what you have to do. This is what you have to do once you are in the examination. Like in examination, you have to find all these things are usually asked in the examination. So, okay, so most of the times you are asked only these questions, like potential inside, potential outside, and all those things. Like this is something that you're going to be asked in the examination. Now, let us take another थोड़ा सा difficult case. अच्छा एक और कर लेते हैं, एक काम कर लेते हैं, चलो एक काम करते हैं पहले. Let us do a problem that makes much sense. So let us take the problem of let us take a classical problem. This is some very classical problem. You will find it in Jackson, probably in your Griffith also you'll find it. Like I will take a conducting sphere placed in a uniform electric field. So if my conducting sphere is placed in a uniform electric field, what can be like what would be the induced charge, and what would be the induced charge on the surface, and what would the potential anyway outside the sphere? All these things are important to us. So that is what we are going to see in this particular discussion. So most appropriately, I'm taking the best coordinate system that I can take, because otherwise the question will become very difficult. So what I would simply take that my sphere is this way. So my sphere is placed in a uniform electric field, and what I will do what, and this is a classical problem. You will find this kind of treatment in many books, so don't worry about it. Okay, so for example, I will say that my electric field is along the z-axis. So what I will do, so along the I'll take my electric field to be along the z-axis. So I'll take my electric field to be along z-axis. So if I take my electric field along the z-axis, what will happen? You know that whenever you talk about this is something that you know, that electric lines of force always enter normally and emanate normally. Like they terminate and emanate normally on the surface of the conductor. Is that clear? So this is how I'm going to make my lines of forces on the surface. And there would be some induced charge, because you know that if your electric field is here and this is a completely uncharged, I'm writing this is uncharged, or you can say neutral. Uncharged, neutral, conducting, whatever you can say, conductor. So you can expect that because of this electric field, there would be some positive charges which will accumulate on the northern hemisphere, and the negative charges will start accumulating on the southern hemisphere. Is that clear?
Yes.
And these induced charges will also slightly distort the external field, because of this induced distribution. You will find some distortion in the electric field, but overall this will be like straight line. But near to the surface, when it comes on the surface, it will enter and it will like terminate or emanate normally. And overall, this sort of distribution you may expect because of the induced distribution. The induced distribution will have certain electric field, so you may expect this kind of thing. So overall, this is something that I've drawn. So this is my electric field along the z direction. So I will simply write E naught z cap, or you can write E naught k cap. So my electric field is along the k cap direction. I have placed an uncharged metallic sphere, or you can say a conducting sphere, in an electric field. And if I have placed this, you can now I know that my electric field would be equals what? My electric field will be equals to E naught k cap. And I've taken spherical polar coordinates, and in spherical polar coordinates, if I write this my electric field as minus dV upon dz, it will be like E naught. So V as a function of Z, I can write it as minus E naught Z, and this will be plus some constant of integration. Is that clear? Okay. So what you can see that your Z in spherical polar coordinates, you know that your Z coordinate, like this is your Z axis, and any distance like radial is this R, and this is theta. So you can write that your Z is equal to R cos theta. In spherical polar coordinates, a radial distance, and this is your Z. So I can write my Z is equal to R cos theta. So you can clearly see that your function V is a function R and theta. So this particular problem will have azimuthal symmetry. So there will be no such phi dependence. So there will be some azimuthal symmetry, and you will see that this particular problem, there will be no such phi dependence. And that you can see, like, that your electric field is along the Z axis. So I'll simply write my dV by dz would be E naught, and I can write Vz would be minus E naught Z plus some constant of integration, and Z I can write it as R cos theta. So overall, I know that my potential as a function of R and theta would be given by minus E naught R cos theta, and there would be some constant that I'll find. For that, I will do something like, either if you see the Griffith has taken it to be 0. So he says that take the potential to be 0, because after all, this is an equipotential surface, so potential on the sphere would be some constant. So he takes, to make the case simple, he takes 0. I'll take some phi naught. That, like, uh, okay, is that clear to you? So this particular problem is a problem of Laplacian equation. Since it is uncharged, so anywhere inside you will not find any charges. And also these charges are induced charges. These are not source. Overall, the total charge is 0. Like, understand my point. Like, this was uncharged, and this because of the presence of the electric field, you can have this kind of induced distribution. And we'll find what these induced distribution of charges look like. Like, we'll find the form of this induced charge distribution also. But overall, understand that this satisfies the condition for the Laplacian equation, or more appropriately, Laplacian equation with an azimuthal symmetry. Is that clear? अभी तक समझ में आई बात?
हाँ भैया.
So I'll write it here itself. So there would be, these are induced charges. Don't get confused. These are induced charges. And as we go along, we'll find what is the form of these like induced distribution. So in terms of R and theta, we'll see that. So since there are no sources anywhere inside outside, so I'll write that my this is a problem of Laplace's equation with azimuthal symmetry. And the solutions to this is given by summation AL R raised to power L plus BL upon R raised to power L plus 1, and then you have this PL cos theta. Okay, is that clear? I think this is clear. Anywhere inside, I cannot have, anywhere inside, we cannot have like BL where L is equal to 0, because if L is equal to 0, then this will be some 1 upon R. And then there would be some 1 upon R kind of term, that is some source term will be inside. Is that clear? So inside, I will not try to keep all these terms. Okay, but outside, now understand, outside, now my potential is not becoming 0 as R tends to infinite. In fact, you can see that as R tends to infinite, my potential is going infinite. Okay, so in this case, we have to be certainly cautious. And the first thing that we should be able to find is potential anywhere outside the sphere. So potential anywhere outside the sphere. This is what we are interested in right now. So potential anywhere outside the sphere, how we can write that particular expression. In this, we are interested. Understand, now things are not that easy that as it seems. So we'll go to matter. Is that clear? Is that not clear? मतलब समझ में आ रहा है नहीं आ रहा है?
हाँ भैया.
Okay. Now for large distances, okay. So for large distances, my potential कहाँ गया यार? My potential as a function of r and theta, ये क्या दे रखा था? Minus e naught r cos theta plus c. Now as r tends to infinite, this will go to zero. I mean, this term will become zero in any case. देखो, r tends to infinite, this term will become zero. Are you getting my point or are you not getting my point? For large distances, these terms will become zero. See, पहले क्या कर रहे थे? Potential outside the sphere के लिए we were only taking these terms. Is that clear? Because as my r tends to infinite, my potential was becoming zero. Now understand, as r tends to infinite, now my potential is infinitely large. So I may take these terms now. In order to find potential anywhere outside the sphere, now I may use this term. I will use this term. I will use this term. Is that clear or is that not clear? देखो, usually क्या कर रहे थे? What we were doing usually, we were just concentrating. Whenever we used to say what is potential outside, we used to take this term. But now understand, potential outside now is tending to infinity as r tends to infinity. So I'm going to take it in general. Is that clear? Now as r tends to infinity, all the terms containing BL, ऐसे लिख देता हूँ, all the terms containing BL will go to zero. Would be zero. Is that clear? So in that particular case, I will have to equate my AL term. So I have to just equate my, we will just compare. We'll compare only terms containing AL. So terms containing AL we have to compare. And if I compare the terms, if I have to see what are the terms comparing, like this will be A naught plus A1 cos theta is equal to minus E naught R cos theta plus C. There is no such term as A2 because there is no such term of cos square theta. So simply A naught will be equals to C. Your A1 will be equals to minus, sorry, at R equals to, अच्छा, A1 R cos theta. So simply A1 would be equals to what? A1 will be equals to minus E naught. अभी तक समझ में आ रहा है या नहीं आ रहा है? Please let me know. Are you getting the difference? See, here your potential is not becoming zero at infinity. So it is tending to infinity. So I have to compare now, and potential at infinity is containing some linear term in R. So linear in R can only be from here. Now no longer I can write my potential outside as BL upon R की power n plus. Is that clear? कोई बोल ही नहीं रहा है. Is that clear? Please let me know.
Yes, sir.
हाँ भैया.
ठीक है. As R tends to infinite, BL is not zero, but these terms are becoming zero. That I cannot help. So from as R tends to infinite, from that kind of condition, I can find only A naught and A1. I have to still find my BLs. Don't worry about it. We will find BLs, but till now, up to this stage, I can write my V as a function of R comma theta. Outside can be simply written as A naught की जगह मैं लिख देता हूँ C minus E naught R cos theta, and then there will be some terms of BL. I'm not saying that these terms will not exist. See, R tends to infinity. Because of this R tending to infinity, this will become zero. I'm not saying that BL is zero. Is that clear? So there will be some terms in BL that we'll see. Is that clear? Now, we know that the conducting surface is an equipotential surface. We know that your conductor is an equipotential surface. The surface of the conductor is an equipotential. Is that clear? So generally, if you see Griffith, he has taken the potential to be zero for convenience. Let us take more general case. So like I will take the potential on the surface as phi naught. However, the answers would remain same. Don't worry. Like answers in terms of induced distribution, induced charge distribution, they will remain same. But potential in general, we'll take phi naught on the surface, so that we remain as general as possible. Although Griffith is also not wrong. He's saying that why not take potential to be zero? Because after all, it is an equipotential surface. So you just take potential zero. So he's also right, but I'm taking it as phi naught. Is that clear? So I know that my potential on surface is phi naught, and I know that potential anywhere outside is given by the above expression. So what I will do, I will simply write at r equals to capital R, this is equal to phi naught. So I'll write E C minus E naught R cos theta, and then I will simply write VL upon R raised to power L plus 1, and this is like PL, and this is cos theta, and summation implied, and this will be like equals to phi naught. Is that clear?
Yes.
Okay. So just we have to what we have to do, we have to equate all these terms. Like we have to equate both of these terms. So what I'll do, I'll simply I know that there is a constant there. So what I will do, this is C minus this is E naught R cos theta plus, and you understand that this particular term will be B1 like L equal to 0, this will be B naught upon R, and then this will be B1 upon R square, and this will be cos theta. Why I'm writing cos theta? Because cos theta is somewhere. So I'm using this cos theta term. Otherwise, all these terms will go to 0. Forget about them. Because you do not have all these terms there. So I'm not writing all these terms. This will be equal to 5. So you have a constant there. So if I write, if I have this constant phi naught written there, I know my constant would be equal to what? Constant C minus B2 upon R cube. It will be there, and this is equals to constant phi naught. And I know that there is no such cos square theta term there, so my B2 would be 0. So in any case, my C would be equals to phi naught. Is that clear? अच्छा एक B naught वाला term भी तो था ना? L equals to 0 प्लेस करेंगे तो there will be some B naught term as well ना? कुछ गलती कर रहे हैं क्या? Are we doing some mistake somewhere?
भैया ये जो पोटेंशियल फाइव नॉट लिया ना ऑन द सरफेस,
हाँ
ये कहाँ से आया? मतलब ये अज्यूम किया क्या किया है? मुझे
देखो,
नहीं पता।
कोई भी मेटेलिक सरफेस होगी, उसका सरफेस हमेशा एक इक्विपोटेंशियल सरफेस होता है. इक्विपोटेंशियल मतलब देयर कुड बी सम कांस्टेंट पोटेंशियल ऑन द सरफेस. So I've just taken it as phi naught. That constant I've taken it as phi naught. Is that clear?
हाँ ओके.
Okay. So my constant, in general, you just you write all these constants like C and B naught are some constant, and this is equal to some phi naught. Forget about it. Like constants, even if you write C B naught plus R also, the B naught plus R also, and even if I expand this particular term, in any way this will be like P naught only. So P naught is again 1. So overall my constants would be equal to some phi naught. Overall, understand my total constants from here would be equal to what? Phi naught. Is that clear? Constant would hardly matter. Like potential wise, you also know that addition of some constant and like deletion of some constant would hardly matter. But overall, I'm saying that constant terms would be equals to what? Fine. Is that clear?
Yes, sir.
Okay. Now next term, what I'm getting is एक थोड़ा सा ध्यान से देखते हैं. Now this is cos theta term is not there, so I will write that my E naught R would be equals to B1 upon R square. Is that clear? So I can write that my B1 would be equals to I think E naught upon R cube. B1 would be equals to E naught upon R cube. This is what we were trying to find. B1 would be equals to E naught upon R cube. Is that clear? So and for all otherwise BL will be 0 for all other L. For all other L. Like for L equal to 0, it will not be like it will be some constant. I have written constant plus constant, again new constant, and that new constant would be final. So forget about constant values, but otherwise BL would be 0 for all other L. That is for all L greater than 1. Is that clear? So B1 we have found. Now we are in a position to write the potential anywhere outside. So potential anywhere outside would be equal to what? It will be equal to phi naught minus E naught R cos theta. And then you have the summation B, all these things. So I know that only B1 survives there. So you have E naught upon R cube. This is your B1. And B1, if you want to write, B1 would be like R square. Like small r square would be here. And then you have this P2 cos theta, P1 cos theta. So this will be like cos theta. I hope it is clear or not clear.
Yes, sir.
Yes.
I hope it is clear. Is that clear? Okay. So overall, I can write my v as a function of r comma theta is some constant phi naught. So what does Griffith do? Griffith says keep it as 0. So uski book mein, if you find, you will not find this phi naught term. But in general, I have written this phi naught. You also know that potential hardly matters because because it all depends on reference. So that is one thing. So what I'll take, I'll simply, in order to maintain some sort of symmetry, what I'll take, I'll take E naught common, and I want to present in the form the Griffith presence. So this is what I'm going to do. Like this is कुछ तो गलती की मैंने B1 कुछ तो गलती एक बार चेक करो B1 क्या आ रहा था B1 is E naught into R cube. वही मैं क्या गलती हुई. So B1 is E naught into R cube. So this is E naught into R cube. एक काम करते हैं ना, एक R भी कॉमन ले लेते हैं बाहर. So we'll take R cos theta outside. So this will be like R cube here. Okay, is that clear? So this is like V r comma theta will be phi naught minus E naught 1 minus R capital cube upon R small cube into R cos theta. Is that clear?
Yes, sir.
Okay. So so for example, when this particular sphere was not present, so when this particular sphere was not present, an electric field was present. So if you write this electric field in the radial direction, in the radial terms, that is, if you don't write E naught k cap, so what would be electric field? Electric field would be equals to what? E naught k cap. E naught k cap, I can write it as E naught k cap. If I want to write, sorry, if I want to write the potential, what would be the potential? It will be minus E naught z, or I can simply write some constant minus E naught r cos theta. This would be potential, even as at r tends to infinity. If you did not have this conductor, electric field was still there. Electric field was present. E naught k cap I can write. So electric field, sorry, potential as a function of r comma theta would be C minus E naught r cos theta, isn't it? So what is the change that has come? So because of this pair, this additional term is appearing. So this certain modification is due to the sphere. This is why I'm writing this, because all these kind of things are asked in your examination, and then you are not able to identify okay. Is that clear? So your electric field, you can say that this particular kind of potential modification will be brought about by the induced field inside. See, हो क्या रहा है? Because of the presence of क्या हो रहा है यार? ठीक है, देखो मेरी बात समझने की कोशिश करो. व्हाट आई वांट टू सजेस्ट इज, देखो अगर ये कंडक्टर नहीं होता, योर इलेक्ट्रिक फील्ड वाज स्टिल देयर. अगर कंडक्टर प्लेस किया, तो जैसे ही कंडक्टर प्लेस किया, बिकॉज ऑफ द एक्सटर्नल इलेक्ट्रिक फील्ड, देयर वुड बी सम induced distribution, and this induced distribution will give rise to some induced electric field inside, isn't it? And this induced electric field would modify my expression of potential. Is that clear or not? So this is the term which I can write like this is the modification brought about by induced electric field. Are you getting my point? Induced हाँ बेटा बोलो.
सर इंड्यूस्ड इलेक्ट्रिक फील्ड ये जो इनसाइड डेवलप हुई है उसकी वजह से ये टर्म आई है ना.
राइट. सोचो
तो
क्योंकि
सर इनसाइड
हाँ बोलो.
इनसाइड
सॉरी,
वाले में तो सर हम एएल वाले टर्म्स कंसीडर करते थे ना,
मैं
जो
नहीं
इनसाइड
समझा.
कंट्रीब्यूशन देता था पोटेंशियल का, वो
हाँ.
एएल एएल आर की पावर एल पीएल कॉस थीटा वाली टर्म देती थी ना, वो तो हमने पूरा इग्नोर ही कर दिया.
नहीं किया. See, for example, see, first understand the point. I'm right now doing potential anywhere outside the sphere, right? Right now
यस सर.
I'm doing the potential outside the sphere. Had this spherical conductor, if this spherical conductor was not present, what was potential anywhere outside? It was this.
पी नॉट आर कॉस थीटा प्लस सी.
Now, because of the presence of this sphere, I know that my potential would now follow del square V equal to 0, and I have equated all these things up, and I found this is my potential outside the sphere. Is that clear? Now my potential outside the sphere is certainly modified. So what is the modification? What is the possible reason for this modification? I'm just trying to tell you that this particular thing may be due to it. I'll prove you this. This will be due to this, because see, inside there will be some. I'm not saying I'm not going to find electric field inside. Right now, I'm concerned with electric field outside the sphere. So electric field outside the sphere, had this not been present, what it would have been? It would have been C minus E naught r cos theta. Because of the presence of this metallic sphere, now your potential anywhere outside the sphere has become something like this. Is that clear? And this particular thing obviously would be because of some source electric field, like some electric field. Because this is because of the external electric field. This is very much clear. C minus E naught r cos theta. This is due to the electric field, external electric field, that E naught k cap.
Okay, sir.
What is this? This is possibly due to the induced electric field inside the sphere. Is that clear or not?
Yes, sir. Yes, sir.
Okay. Now, let us first find what will be the electric field. So that will solve a little bit of your problem. So what will be the electric field? So electric field is given by what? It is given by minus of grad of V. And now understand this is a function of r and theta. So it will be written as minus r cap del by del r plus theta cap 1 upon r del by del theta. And then you have this VR, sorry, negative r, VR comma theta. Is that clear? So if I want to find my electric field would be equals to what? My electric field, you just like check it up. I'm just writing it over here because I'm having some lack of time. So electric field will be equals to, I think, E naught. And this will be like 1 plus 2 capital R cube divided by small r cube cos theta. And then you have this r cap. Then I think this is minus. Then you have some E naught. I think 1 minus capital R cube upon small r cube. I'm leaving it to you as a homework. I think this is something that you could do. So electric field would be this way. E naught 1 plus 2 r cube upon small r cube cos theta r cap minus E naught 1 minus capital R cube upon small r cube sin theta theta. Is that clear?
Yes, sir.
And what would be the induced distribution? See, what would be the induced distribution? That is something that we were interested in, right? That is something that we were interested in. So what would be the induced distribution? So because of this external electric field, there will be some induced distribution, right? There could be some induced charges on the surface inside somewhere, right? Is that clear? So this charge density on the sphere, how to find? So I know that, just outside the sphere, or just on the sphere, just outside the sphere, I can write my sigma to be equals to what? I can write sigma upon epsilon naught as En. Is that clear? So if I make this kind of surface, and here you have this distribution of, so just outside you can find your electric field to be equals to what? Electric field to be equal to sigma upon epsilon naught. Electric field to be equal to sigma upon epsilon. So the normal component of electric field would give me an idea of what is the induced distribution. So what is the normal component? So normal to the sphere is the radial direction. Normal to the sphere is the radial direction. Okay, so you have electric field in both two directions, that is in the theta cap and in the r cap. What is the normal to the sphere? Normal to the sphere, you will have this r cap direction, isn't it?
Yes, sir.
So what will be the normal component? Normal component will be the radial component, and that also we want to find at r equals to r minus. If you want to write, you can write r minus, but in any case, this is like tending to r. So if r tends to r, this will be like E naught, and this is r. If you place here, r cube cancel, 3 E naught cos theta. And then what will be sigma? Sigma will be equals to 3 epsilon naught E naught cosine theta. So this is the induced distribution, and you can see that induced distribution is 3 epsilon naught E naught cos theta. And from here you can find the charge. So what will be the charge? Like charge, if I just want to find on the upper side, if I want to find on the upper side, this will be like 3 epsilon naught, because overall total charge would be 0. So understand, I'm just finding on the upper side, and jitna upper mein hoga utna hi lower hoga. So on the upper side, in like I can make a patch. Okay, on the upper side, I want to find what would be the total charge. So charge would be equal to sigma into ds. Is that clear? Okay, and if I'm talking about hemisphere, I know that what I should say. I know that my theta would vary from 0 to pi by 2, and my phi would vary from 0 to 2 pi. So I would simply integrate it from सॉरी थीटा है, थीटा 0 से लेकर थीटा पाई बाय 2, दिस विल बी लाइक cos थीटा sin थीटा d थीटा इंटीग्रेशन 0 to 2 pi d phi. Is that clear or is that not clear at all?